What if the greatest lie a continent ever told was its color? We see Antarctica as the last great white, an immaculate expanse of impossible purity, an entire continent entombed in ice, a fortress of solitude at the bottom of the world. It is a place defined by its cold, a cold so profound, so absolute, it feels like a fundamental law of the universe, not merely an absence of heat. This is the story we have always told ourselves. The story of a polar desert, static and eternal, the Earth's cryospheric heart, beating with a rhythm so slow it is measured not in seconds but in millennia. But this story, like the pristine surface of the ice itself, conceals a violent, fiery secret. Beneath this serene frozen mask, the seventh continent is burning. It is a land of paradox, of fire and frost, locked in an ancient secret war. And we are only now beginning to understand the terrifying implications of who is winning. From orbit, the scale is almost incomprehensible. A single continuous sheet of ice, larger than the United States and Mexico combined, draped over mountains we cannot see and canyons we have never explored. This colossal reservoir of frozen fresh water holds 90% of the world's ice, a quantity so vast that if it were to melt, it would raise global sea levels by nearly 200 feet. For generations, we viewed it as a planetary thermostat, a stable anchor in a changing world. We measured its slow glacial creep towards the sea, we charted its seasonal ebb and flow, and we believed we understood its nature. It was the sleeping giant, and our climate models assured us it would take thousands of years to awaken. But the giant is stirring, and it is not waking slowly. Across the continent, the symphony of stillness is being shattered by a crescendo of collapse. You are witnessing it now. Rivers of sapphire blue meltwater carve through ice that has not seen the sun for 1,000,000 years. Vast lakes, larger than entire cities, form and then vanish in a matter of days, draining through newly opened crevasses with the force of 1,000 Niagaras. Great tongues of ice glaciers that have served as monolithic dams for eons are accelerating their inexorable march to the ocean, quickening to a frantic sprint. And at the coastline, the final dramatic act unfolds. Ice shelves, floating platforms of ice the size of nations, are disintegrating. They shatter into armadas of icebergs, a flotilla of frozen ghosts set adrift. This is not the gentle, cyclical process of nature we once documented. This is a hemorrhage, a cataclysmic bleeding of a continent's lifeblood into the global ocean. The immediate culprit, the one that dominates our headlines and fuels our anxieties, is of course a character we know all too well. A warming atmosphere heavy with the byproducts of our own civilization settles over the polar cap, raising surface temperatures degree by agonizing degree. Simultaneously, the world's oceans, having absorbed the vast majority of our planet's excess heat, are sending warmer currents to gnaw at the continent's edges. These currents, relentless and unseen, are like a celestial blowtorch applied to the ice shelves' vulnerable underbellies, melting them from below, thinning them, weakening their grip on the seafloor. This is the established narrative, the scientific consensus, and it is undeniably true. The evidence is overwhelming. Human-induced climate change is the primary driver, the great accelerator of this crisis. It provides a complete and completely terrifying explanation for so much of what we are witnessing. And for a time we thought it explained everything. But science is a restless discipline. It is a process of relentless questioning, of probing at the edges of certainty. And deep within the data streams pouring back from Antarctica, scientists began to detect a whisper of something else. An anomaly, a ghost in the machine. The models, as powerful as they were, had a persistent flaw. They were consistently underestimating the speed and the ferocity of the melt. They could predict the general trend, but they couldn't account for the terrifying velocity of the reality. There was a missing variable, an unknown force that was adding its weight to the scales, tipping the balance far faster than our worst-case scenarios had ever dared to predict. The mystery was not just one of speed, but of location. The most catastrophic melting wasn't always happening where the warmest air or the most aggressive ocean currents were found. In some of the most remote, bitterly cold and seemingly stable regions of the vast East Antarctic ice sheet, places that should have been safe for another 10,000 years, the ground beneath the ice was inexplicably sinking. The ice was melting profoundly and unstoppably from the bottom up. Imagine the frustration. You are a scientist in a state-of-the-art lab, thousands of miles from the ice. You have satellites that can measure a change in elevation to within a fraction of an inch. You have seismic sensors, ice-penetrating radar, and gravity anomaly detectors. You have built the most sophisticated virtual Earth imaginable inside a supercomputer. You input the known physics, atmospheric temperature, ocean circulation, snowfall, ice mechanics. You press run. And the simulation returns a world that is dangerously, stubbornly different from the real one. It's like trying to solve a celestial murder mystery where the murder weapon is missing, and the prime suspect has a verifiable alibi for half the crimes being committed. The ocean and the air were accomplices, yes, but they were not acting alone. There was another agent at work, a hidden perpetrator operating from a place we couldn't see deep beneath 3 miles of solid ice. For decades, this remained the great unsolved problem in polar science, a persistent nagging dissonance between theory and observation. Theorists proposed ideas, some bordering on the heretical. Could there be networks of subglacial rivers lubricated by immense pressure and friction, creating thermal highways that channeled heat across the continent? Could there be unknown variations in the Earth's geothermal flux hotspots in vase, the crust that were flaring up beneath the ice? For reasons we couldn't fathom, each theory was a shot in the dark, a desperate attempt to illuminate a problem space that was by its very nature shrouded in impenetrable darkness. You can't simply go and look. You can't drill thousands of holes through the coldest, windiest, most hostile environment on the planet. The continent guards its secrets with a ferocity that has humbled every generation of explorer. To find the answer, to uncover the real reason for this terrifying melt, we would need more than just better models. We would need a new way of seeing. We would need to peel back the skin of the world and look at the fire within. This is where our story truly begins. It begins with a project so ambitious, so technologically audacious, that it was spoken of in hushed tones at scientific conferences for years before it became a reality. It was a coordinated international effort, a kind of Manhattan Project for the earth sciences, uniting geophysicists, glaciologists, seismologists, and data scientists. Its codename was 3I, Atlas, the 3I standing for Interferometric Ice Investigation. Atlas, for Antarctic Tectonic and Lithospheric Analytical Survey. The name itself is a mouthful, a piece of technical jargon that belies the revolutionary poetry of its mission. 3I, Atlas, was not designed to look times at times the ice. It was designed to look times through times it, to use the entire 3-kilometer thick ice sheet as a colossal lens focusing on the secrets of the Earth's crust and mantle hidden beneath. It was a continental-scale MRI, an ultrasound for a sleeping planet. The plan involved deploying a vast, invisible network of hundreds of hypersensitive seismic and gravitational sensors, some buried deep within the ice itself, others listening from the bedrock at its periphery. This network would not just listen for the groan of shifting ice or the tremor of distant earthquakes. It was designed to listen for something far more subtle. It was designed to listen to the very heartbeat of the planet's deep interior. By measuring the impossibly faint gravitational pulls and the minuscule travel time variations of seismic waves passing through the rock miles below Atlas, could construct a 3-dimensional map of the continent's hidden geology. It could map density. It could map temperature. It could finally see the heat bleeding from the Earth's core into the crust. For the first time, we were not just guessing what lay beneath the ice. We were preparing to see it. The teams who deployed these instruments were undertaking a mission on the ragged edge of possibility. They worked in conditions that mimicked the surface of another planet, in temperatures that could freeze exposed skin in seconds and where the wind never ever stopped. They drilled for weeks into the ancient compressed ice, lowering delicate instruments into boreholes, hoping the immense pressure wouldn't crush them. They built autonomous power stations in the middle of a white void, knowing they had one chance to get it right before the long polar night descended for 6 months. It was a monumental gamble, a billion-dollar bet on the belief that a hidden truth was waiting to be found. For years, the Atlas network sat in silence, listening. It patiently collected a torrent of data, a flood of petabytes so immense that new forms of artificial intelligence had to be developed just to sift through the noise and find the signal. Scientists waited, watching the patterns emerge bit by agonizing bit. They were searching for the signature of a hidden heat source, a geothermal anomaly. What they found was so much more. The data from 3I, Atlas, did not reveal a simple hotspot. It did not uncover a mere geothermal curiosity. What it unveiled was a structure, a vast continent-spanning geological feature whose existence had never been predicted, whose power had never been factored into our climate models, and whose influence on the ice sheet above was profound and terrifying. It was not a passive feature, not just a place where the crust was thin. It was active, dynamic, a living, breathing system that pulses with the primeval heat of our planet's formation. This is the real reason teased in our title. The missing perpetrator in the mystery of Antarctica's accelerating collapse. It is a force that has been shaping the continent for hundreds of millions of years, long before the first snowflake ever fell upon its mountains. And now, in a moment of terrible cosmic coincidence, its ancient cyclical rhythm is aligning with the new frantic warming we have created on the surface. The two forces, one from deep within the Earth and one from the sky above, are beginning to synchronize. They are forming a devastating partnership, a pincer movement of heat assaulting the ice from both above and below. Our story is not about dismissing the threat of climate change. It is about revealing that the situation is far more complex and far more urgent than we ever imagined. The sleeping giant is not just being nudged awake by a warming blanket. It is being shaken from its slumber by a fire raging in its own basement. To understand what Atlas has shown us, we must fundamentally reframe our perception of Antarctica. We must learn to see it not as a static block of ice, but as a thin, fragile crust separating two immense and powerful thermal engines, the sun above and the planet's core below. The fate of our coastlines, of our cities, of our civilization may depend on understanding the battle between them. The journey we are about to embark on will take us deep into the invisible world beneath the ice. We will explore the anatomy of this newly discovered geological behemoth. We will trace its history back through deep time to the age of dinosaurs and the shattering of the supercontinents. And we will confront the unnerving question of what happens next. What happens when the planet's own internal furnace begins to work in concert with our warming world? The first data stream from the Atlas network has given us the map of this hidden underworld. Now we must venture into it. What if the most profound change to our world, the ghost in our climate machine, was not born in our skies or in our seas, but was delivered from the silent, frozen depths of interplanetary space? This is a story about a key turning in a lock we never knew existed, a story that begins not with a bang, but with a slow, almost imperceptible thaw at the bottom of the world. It begins in Antarctica. To understand our future, we must first journey to this place, this continent of superlatives. It is the coldest, the driest, the highest, and the most remote land on Earth, a realm so alien it has long served as a proxy for other worlds. But Antarctica is not some distant, irrelevant wasteland. It is the planet's great white heart, a colossal pump in the circulatory system of global climate. Its very existence, its sheer blinding whiteness, reflects immense amounts of solar energy back into space, acting as Earth's primary cooling system, a planetary air conditioner. Its frigid winds and the cold, dense water sinking from its shores drive the engine of ocean currents that regulate temperatures across the entire globe, from the monsoons of Asia to the temperate winters of Europe. You feel its influence in the air you breathe, in the food you eat, in the fundamental stability of the world you have always known. Antarctica is the silent gravitational anchor of our climate system, and it is a behemoth built of ice. The sheer volume is a concept that defies human scale. Imagine the entire contiguous United States from California to Maine buried under a sheet of solid ice nearly 2 miles thick. Now add another half. This is the Antarctic ice sheet. 90% of all the ice on planet Earth is here. 70% of all the world's fresh water is locked away in its crystalline structure, a planetary reservoir holding the memory of ancient snowfalls, each layer a frozen page in the long epic story of our world's climate. Contained within this single immense glacier is the power to remake our coastlines, to redraw the maps of human civilization. If all of it were to melt, global sea levels would rise by nearly 200 feet. 200 feet. It is a number so catastrophic that it feels like fiction. London, Amsterdam, Shanghai, Miami, New York submerged. Billions of people displaced. The world as we know it drowned. For generations, this apocalyptic scenario was just that, a distant abstract fear, a theoretical possibility for a far future humanity to worry about. The ice sheet was seen as a permanent fixture, an eternal monument of our world, too vast, too cold, too indestructible, to be seriously threatened on any timescale that mattered to us. We believed it was eternal. We were wrong. Our scientific relationship with this southern continent is surprisingly young, a story of courage, curiosity, and a slow dawning comprehension. For centuries, it was Terra Australis Incognita, the unknown southern land, a myth on the fringes of maps, a cartographer's fantasy. The first humans to set eyes on it did so only 2 centuries ago, and the first to stand at the geographic South Pole a little over one. These early expeditions, sagas of heroic endurance against unimaginable hardship, were quests of geography and national pride. Their goal was to chart the coastline, to claim territory, to simply survive. The ice itself was the enemy, the obstacle, a monolithic, featureless barrier to be crossed, not understood. The science was rudimentary, focused on weather magnetism, geology, glimpsed in the few bare mountains that pierced the ice like the bones of a buried giant. The true nature of the continent, the world, times under times, the ice remained as mysterious as the surface of Mars. The great shift began in the mid-20th century with the International Geophysical Year of 1957 to 58. It was an unprecedented global scientific collaboration born from the tensions of the Cold War that saw humanity turn its gaze collectively upon its own planet. Antarctica became a continent for science, a natural laboratory of unparalleled scale. Dozens of research bases were established, permanent footholds in the deep cold, and for the first time our questions changed. We were no longer just asking what is here, but how does this work? How deep is the ice? How old is it? Is it moving? Is it changing? These were the foundational questions, and answering them required a new generation of tools. Scientists drove massive tractor trains in long, arduous traverses across the ice cap, using seismographs and explosives to measure its thickness. They drilled the first deep ice cores, painstakingly extracting cylinders of frozen history that allowed them to read the planet's past climate like a book. They were building the first coherent picture of this immense dynamic system, sketching the initial outlines of a giant that was slowly beginning to awaken. But even then, through the 60s and 70s, the prevailing view was one of glacial slowness. Ice sheets, the textbooks taught, respond to climate change over millennia, not decades. They possessed an immense thermal inertia. They were too big to fail, and too big to fail quickly. The concerns of a warming planet were focused elsewhere, on retreating mountain glaciers, on thinning Arctic sea ice. Antarctica, we thought, was safe. It was simply too cold to melt. The advent of the satellite era shattered that complacency forever. Beginning in the late 1970 seconds, eyes in orbit gave us a perspective that was previously impossible. We could now see the entire continent at once, continuously. We could measure the precise elevation of the ice surface, watch its edges advance and retreat, and track the speed of its colossal ice streams as they flowed towards the sea. And as the data began to pour in through the 1,980 seconds and 1,990 seconds, a deeply unsettling pattern started to emerge from the noise. The giant was not sleeping. In certain places along its vulnerable western flank, it was stirring, and it was losing weight. The rate of ice loss was small at first, at the very edge of our ability to measure it, but it was unambiguous, and it was accelerating. The eternal continent was changing, and it was changing within our lifetimes. This realization sent a shockwave through the scientific community. The old models, the ones that spoke of millennial timescales, were wrong. Something was happening, and we needed to understand it. The search for a culprit began, and 2 primary suspects quickly emerged, both born from the simple, intuitive physics of a warming world. The first suspect was the atmosphere. This was the most straightforward explanation, the one that made immediate sense to everyone. Greenhouse gases are trapping more heat in the atmosphere. The planet is warming, and ice melts when it gets warm. We could see this process dramatically unfold on the Antarctic Peninsula, the long, slender arm of the continent that reaches up towards South America. Here, where temperatures were rising faster than almost anywhere else on Earth, the effects were stark and undeniable. Vast, ancient ice shelves, floating platforms of ice the size of small countries, were shattering and collapsing in spectacular fashion. Summer melt ponds, a brilliant sapphire blue against the stark white, would form on the surface of the ice. This meltwater would then trickle down, filling crevasses and cracks. But water is denser than ice, so it acted like a wedge, forcing the cracks deeper and wider with immense hydrostatic pressure. This process, known as hydrofracturing, could dismantle an entire ice shelf in a matter of weeks, a geological structure that had been stable for more than 10,000 years gone in a single season. The Larsen B ice shelf collapse in 2002 became the poster child for this mechanism, a shocking, visceral demonstration of atmospheric warming at work. It was a compelling and terrifying narrative. The air was warming, attacking the ice from above, turning its surface into a slushy, cracked battlefield. For many, this was the whole story. It was simple, it was visible, and it fit our understanding of cause and effect. But for the scientists looking at the data from the entire continent, it wasn't enough. The most significant ice loss, the changes that truly threatened catastrophic sea level rise, wasn't happening on the peninsula. It was occurring in the vast, remote basins of West Antarctica, in places so brutally cold that significant surface melting was, and still is, almost non-existent. The atmospheric blowtorch, while potent, couldn't be the primary driver here. There had to be another culprit. The second suspect was the ocean. If the attack wasn't coming from above, perhaps it was coming from below. Antarctica is not just a continent of land and ice. It is a continent surrounded by ocean, and much of its ice sheet does not end at a coastline. Instead, it flows past the land, extending out over the sea, in the form of those massive floating ice shelves. These shelves are critically important. They act like a cork in a bottle, a buttress that braces the land-based glaciers behind them, slowing their inexorable flow to the sea. They are the gatekeepers. And they are uniquely vulnerable to the ocean. For decades, we knew that a layer of warmer, saltier ocean water, known as circumpolar deep water, lurked hundreds of feet below the frigid surface of the Southern Ocean. It was a reservoir of immense thermal energy, a layer of heat that had historically been held at bay, prevented from reaching the Antarctic coast by winds and currents. But as the global climate changed, the protective winds that held this warm water offshore were shifting and weakening. Like a key turning in a lock, this subtle change in atmospheric patterns was allowing this warmer water to spill onto the shallow continental shelf, to push inward, and to flow into the hidden cavities beneath the ice shelves. You can't see this process from space. You can't even see it from a ship. It happens in the dark, a silent, relentless assault. This intruding seawater, several degrees above freezing, was acting like a celestial blowtorch, melting the ice shelves from their undersides. It was eroding the very foundations of the ice sheet, thinning the shelves, weakening their ability to hold back the colossal glaciers behind them. The grounding line, the critical point where the ice sheet lifts off the bedrock and begins to float, was being eaten away, forced to retreat inland. As the buttressing shelves weakened and the grounding lines retreated, the glaciers behind them began to accelerate, dumping ice into the ocean at an ever-increasing rate. This was a far more insidious and potentially far more dangerous mechanism than surface melt. It was attacking the system at its most vulnerable point. It explained the terrifying changes we were seeing in West Antarctica, in the Amundsen Sea sector, where glaciers like Thwaites and Pine Island were thinning and accelerating into a state that some scientists feared was an irreversible collapse. The case seemed closed. A two-pronged attack, a warming atmosphere assaulting the edges, and a warming ocean undermining the foundations. Together, they painted a complete and devastating picture of Antarctica's future. It was a logical, evidence-based conclusion, and it became the consensus view for years. It just wasn't the whole truth. The greatest limitation, the flaw in this seemingly perfect theory, was that our understanding was built entirely on what we could see from the outside. Our satellites measured the surface. how ships and robotic submarines measured the edges, how models simulated the atmosphere and the ocean. But the vast interior of the ice sheet, the critical boundary between a mile of ice and the continent of rock beneath it, remained almost entirely invisible. It was a world we could only guess at a geological black box the size of a continent. What was actually happening at the base of this 2-mile-thick glacier? Was it frozen solid to the bedrock below as many models assumed? Or was it sliding on a thin film of meltwater lubricated and mobile? Was the rock itself a static frozen slab of geology, or was there something else happening deep within the Earth's crust? These were not trivial questions. The answers would fundamentally change our understanding of how an ice sheet behaves, how quickly it can respond to change, and how vulnerable it truly is. For decades, our only window into this hidden world came from a single ingenious technology: ice-penetrating radar. By sending radio waves down through the ice, from airplanes flying high above, scientists could map the shape of the bedrock below, creating the first ghostly outlines of the subglacial landscape. And what they found was astonishing. Beneath the monotonous flat white surface lay a world of immense complexity. There were vast mountain ranges, the Gamburtsev Mountains as large as the European Alps, entirely entombed in ice. There were deep canyons, river valleys, and vast basins. And then, in the 1,970 seconds, the radar revealed something utterly unexpected, something that sounded like science fiction liquid water. In central East Antarctica, the coldest place on Earth, the radar signals showed a perfectly flat reflection, the unmistakable signature of a water surface. It was a lake the size of Lake Ontario buried under 2.5 miles of solid ice. We would later name it Lake Vostok. This discovery was a paradigm shift. The base of the ice sheet was not a simple frozen boundary. It was a complex dynamic hydrological system. The immense pressure of the ice above lowered the melting point of the water, while the Earth's own geothermal heat, flowing up from the planet's core, provided just enough energy to keep it from freezing. We had discovered a hidden world, and it was a world teeming with possibilities. If there was one lake, there could be others, and there were. Subsequent surveys revealed a network of hundreds of interconnected subglacial lakes, rivers, and streams, a vast continent-spanning plumbing system hidden completely from our view. Suddenly, we understood that water at the base of the ice sheet could act as a lubricant, allowing the ice to slide faster to respond more quickly. The black box was beginning to open, but each new revelation only deepened the central mystery. We had accounted for heat from the air and heat from the ocean. But we had barely begun to consider a third, far more enigmatic source: heat from the Earth itself. The continent was alive underneath in a way we had never imagined. But our models of this geothermal heat were crude, based on global averages assuming a uniform passive continent. We were still missing a crucial piece of the puzzle, a hidden variable that could explain why certain regions were melting so much faster than others. We were looking for a terrestrial explanation, a geological smoking gun hidden beneath the ice. We were searching in the right place, but for the wrong reason. We were about to learn that the real secret to Antarctica's accelerated melt was not a story about geology, but a story about cosmology. The key to the future of our planet was not buried in the Earth's crust, but was written in the trajectory of a forgotten visitor from the outer solar system, a silent messenger that had delivered its cargo 500,000 years ago, leaving behind a wound that is only now beginning to bleed. We had reached an impasse, a wall of white stretching to the horizon and plunging miles into the crushing dark. Our atmospheric models were broken, our theories of ocean circulation were proving tragically incomplete. The engine of this catastrophic melt, the ghost in the machine, was not in the sky above, but in the unknown abyss below. To see what lay behind that icy veil, to map the arteries of a hidden world, we couldn't just build a better satellite or a more sensitive thermometer. We had to do something unprecedented, something audacious. We had to build a key for a lock that had never been turned away to pierce the heart of the world's last unexplored continent. What emerged from drawing boards in labs from Pasadena to Cambridge was more than just a mission. It was a confrontation, a grand, multi-pronged assault on ignorance, conceived on a scale as vast as Antarctica itself. It was given a name that conveyed both its ambition and its purpose: 3I Atlas. The ice sheet interior imaging, Antarctic Thermal Layer Assessment System. It was our gamble to pull back the curtain once and for all. Atlas was not a single instrument, but a technological ecosystem, a triad of interlocking systems designed to work in concert, each providing a unique piece of an impossible puzzle. It was a nervous system we intended to lay across the bottom of the world, designed to feel, to see, and to listen in a realm where humanity could not survive. The first pillar of this triad was perhaps the most intuitive, yet the most daring, a fleet of autonomous underwater vehicles, our eyes and ears in the frigid, lightless ocean churning beneath the colossal ice shelves. These were not clumsy, tethered robots. They were sleek, intelligent predators of the under-ice ocean, torpedo-shaped leviathans of titanium and composite, engineered to hunt for truth in the perpetual twilight. We called the flagship of this fleet Times Taniwha Times after a mythical Maori guardian of the deep waters, and she was a marvel. Over 20 feet long, with a mission endurance of months, not hours, Times Taniwha Times, and her sisters were designed for a level of independence no submersible had ever achieved. Their primary challenge was navigation. Far from the guiding light of GPS satellites, lost beneath a canopy of ice, 3/4 of a mile thick, they had to feel their way forward like a blind person in an unfamiliar room. They would rely on a revolutionary form of terrain-relative navigation, bouncing sonar signals not off the seabed but off the ice ceiling above. This inverted world became their sky, a jagged, inverted mountain range of pressure ridges and melt channels, which they would meticulously map. An array of interferometric synthetic aperture sonars, usually reserved for military spycraft, would paint a breathtakingly detailed picture of this chaotic interface, revealing every fissure, every terrace, every single point where warmer, ocean water was licking away at the continent's frozen shield. But seeing the ice was only half the battle. They also had to taste the water. Tucked within their hulls were miniaturized mass spectrometers and isotope analyzers, sophisticated chemical laboratories capable of sniffing out the faintest geological clues. They would hunt for traces of helium-3, a primordial isotope that bleeds only from the deep earth, a definitive fingerprint of volcanic activity. They would search for chemical signatures of hydrothermal vents, for telltale gradients in salinity and temperature that could betray the location of a hidden river of subglacial meltwater pouring into the sea. Each AUV was a pioneer tasked with venturing into a cathedral of darkness whose scale dwarfed any cavern on Earth, knowing that a single software glitch, a single collision with an uncharted ice keel, would mean being lost forever, a silent monument to overreach, entombed in the Antarctic dark. The stakes were absolute. The team that designed them knew that releasing these machines was an act of faith, letting their creations go to map a world they themselves would never see. The second pillar of the Atlas project was designed to go where even the AUVs could not directly through the ice itself. If we were to understand the continent's plumbing, we needed to place sensors at the source, at the critical boundary layer between ice and rock. This required an instrument of brute force and exquisite finesse, the deep-drilling subglacial probe system. The challenge is almost paradoxical. How do you drill a hole through 2 miles of ice in temperatures that can drop to 100 degrees below zero without your borehole instantly freezing shut behind you? The answer was a technology perfected over decades of polar research, but now supercharged for the Atlas mission, the hot water drill. It is less a drill and more of a controlled high-pressure descent into the abyss. A massive array of heaters would raise colossal amounts of melted snow to near boiling, pumping the water down a reinforced hose at immense pressure. This celestial blowtorch, wielded with surgical precision, would melt a narrow portal, a temporary artery connecting our world on the surface to the alien world 2 miles below. The process is a frantic race against the planet's thermodynamics. Drill too slowly and the cryostatic pressure of the ice sheet, the sheer weight of a continent, will squeeze your borehole closed. Drill too fast and you risk creating a cavern so large it destabilizes the surrounding ice. The team had to perfect a delicate ballet of pressure, temperature and speed, maintaining a stable liquid-walled tunnel for just long enough to deploy their payload. And what a payload it was! The probes themselves were not drills but sentinels. Each was a slender, hardened cylinder, packed with the most sensitive instruments we could devise. Once the drill head broke through the base of the ice, the probe would be released, designed to embed itself at the ice-bedrock interface, the ground zero of the melting phenomenon. For the first time, we would have a permanent presence there. These probes were our remote nerve endings. They carried high-resolution thermometers capable of detecting temperature fluctuations of less than 1,000th of a degree, signaling the faintest pulse of geothermal heat. They housed pressure sensors to measure the flow of subglacial water, revealing the ebb and flow of hidden rivers and the filling and draining of vast unseen lakes. Seismometers within them would listen for the faintest tremors, the microquakes generated by grinding rock, shifting ice, or perhaps something else entirely. Each probe was also a chemist. Microfluidic labs on board would continuously sample the basal water, analyzing its geochemistry for the telltale signs of rock-water interaction, searching for the unique mineral signatures that could only come from a deep, magmatic heat source. Deploying them was an ordeal. A small city had to be erected at each drill site in the harshest environment on Earth, a city dedicated to the singular purpose of opening one of these fleeting windows to the deep. Every successful deployment, every probe that came online and began transmitting its precious data, was a victory against the colossal indifference of nature, a single point of light in an immeasurable darkness. The third and final piece of the Atlas triad was the one designed to see it all, to connect the dots provided by the AUVs and the deep probes. We needed a way to create a complete three-dimensional map of the entire subglacial world, the shape of the bedrock, the thickness of the ice, the location of hidden water systems across millions of square kilometers. We needed a continental-scale ultrasound. This was the task of the advanced seismic imaging arrays. The principle is simple, but the execution is monumental. You create a sound, a powerful vibration at the surface, and you listen for the echo. The time it takes for that sound to travel down through the ice, bounce off the rock below, and return to your sensors reveals the ice's thickness with stunning precision. But Atlas took it further. Instead of just one source and one sensor, we would deploy a vast grid of them, hundreds of portable seismographs laid out across the ice in a sprawling geometric pattern. And the sound source wouldn't be a simple thump. We would use specialized low-frequency vibrator trucks, behemoths, on tracks that could be precisely controlled to send specific seismic chirps deep into the ice sheet. By coordinating the vibrations and listening with the entire network of sensors, a process known as seismic tomography, we could do more than just measure depth. We could begin to discern the very character of what lay beneath. Just as a medical ultrasound can distinguish between bone, muscle, and fluid, our seismic arrays could differentiate between hard, crystalline bedrock and softer, water-saturated sediments. They could reveal the presence of vast subglacial lakes, which would appear as distinct, flat, highly reflective surfaces. They could map out the ghostly channels of ancient river systems carved into the rock millions of years ago and now buried under a vertical mile of ice. The sheer logistical effort was staggering. Teams of glaciologists and engineers would spend months in the Antarctic interior, living in mobile camps, methodically deploying these sensor grids sector by sector. They would drive the vibrator trucks in precise, pre-calculated lines, pausing every few hundred meters to send another pulse of energy into the planet, painting a picture of the hidden landscape one pixel at a time. The computational power required to process the resulting data was equally immense. Terabytes of raw acoustic information had to be crunched by supercomputers using complex algorithms to filter out noise and interference, slowly resolving the echoes into a coherent image. This seismic array was the backbone of the entire project, the Grand Cartographer. It would provide the context for everything else. When an AUV detected a plume of warm, mineral-rich water beneath an ice shelf, the seismic map would show us if it was emanating from a deep, previously unknown subglacial trench. When a deep probe registered a sudden spike in temperature, the seismic data would tell us if it was sitting atop a thin crust of rock, a potential weak point in the Earth's mantle. Atlas was a system of systems, a technological trinity, each part essential, each part revolutionary, all aimed at a single goal: to make the invisible visible. The confrontation began not with a bang, but with the quiet hum of servers and the groan of ice under the weight of machinery. The first deployments were fraught with the brutal reality of Antarctica. An early test of the times, Taniwha Times AUV, saw its guidance system nearly crippled by an unexpectedly powerful under-ice current, forcing a frantic last-minute recovery before it could be swept into an inaccessible cavern. The first hot water drill operation was delayed for 3 weeks by a series of relentless katabatic storms, winds so fierce and so cold they threatened to snap steel and freeze hydraulic lines solid. The environment was an active adversary, constantly testing our resolve, our ingenuity, and our equipment. But perseverance paid off. The systems one by one began to come online. The seismic arrays started their slow, methodical scanning. The first deep probes successfully reached the bedrock, their faint signals a beacon of success from the bottom of the world. And Taniwha Times, along with its sister AUVs, embarked on its first mapping missions beneath the Thwaites Glacier, the so-called Doomsday Glacier, whose stability was of paramount concern. For months, the data trickled in. It was a deluge of numbers, waveforms, and chemical readings that had to be painstakingly calibrated, cross-referenced, and analyzed. At first, much of what we saw confirmed our models, but with far greater detail. The seismic surveys unveiled breathtaking landscapes of buried mountains, the Gambutsev Range as jagged and majestic as the Alps, all entombed in ice. The AUVs mapped the underside of the ice shelf with chilling precision, revealing vast, cathedral-like melt channels where warm ocean water was eating away at the glacier's foundation. It was vital work, a revolutionary new atlas of this hidden world, but it wasn't the answer we were looking for. The heat from these ocean currents, while significant, still didn't add up. It couldn't fully account for the speed of the melt, for the slipperiness at the glacier's base that was accelerating its slide into the sea. The real mystery remained unsolved. Then the first anomalies began to appear. They weren't dramatic headline-grabbing discoveries, but subtle whispers in the data inconsistencies that at first were dismissed as instrument error or signal noise. One of the deep probes designated Sentinel-7b Trafe, located in a geologically unremarkable basin far from the coast, began to register a thermal pulse. It was a tiny variation, just a few hundredths of a degree, but it was rhythmic, pulsing with a slow, steady beat like a slumbering heart. It made no geological sense. Another team analyzing the seismic reflection data from the vast expanse of Wilkes Land found something that gave them pause. In one sector, the echoes returning from the bedrock were wrong. They were smeared, distorted, as if the seismic waves had passed through a zone that wasn't quite solid rock, but something less dense, something mushy. It was a region nearly 60 miles across, and our instruments showed it was located deep beneath the thickest part of the East Antarctic ice sheet. Most unsettling of all was a water sample retrieved by Taniwha Times from a deep cavity beneath the Thwaites ice shelf. The initial analysis showed the expected mix of glacial meltwater and circumpolar deep water, but when the mass spectrometer looked closer, it found isotopes of radon and sulfur in concentrations that were completely off the charts. These were short-lived isotopes, meaning they had to have been introduced to the water very recently, and their specific signature didn't match seawater or the bedrock or any known volcanic chemistry in the region. It was a chemical fingerprint without a culprit, a message from a source we couldn't identify. Each of these data points, taken in isolation, was a curiosity, a puzzle for a graduate student to solve. But taken together, they began to paint a disturbing picture. These were not random errors. They were fragments of a single underlying phenomenon, a pattern emerging from the noise. The steady thermal beat from Sentinel-7b, the strange seismic anomaly in Wilkes Land, the impossible water chemistry under Thwaites, they were all pointing to the same terrifying conclusion. The heat source we had come to find was not some passive, slow-bleeding patch of thin crust. What was down there stirring in the deep was something far more complex, more concentrated, and infinitely more active than we had ever dared to imagine. The Atlas system, our grand machine built to answer a question, had instead uncovered a profound and alarming new mystery. And so we waited. For months that bled into a year, the network we had buried in the coldest, most unforgiving place on Earth remained a silent sentinel. The 3i Atlas Array, our intricate web of seismic, thermal and gravitational sensors, was a promise whispered into the deep, a technological prayer sent down through kilometers of solid ice. On the surface, our teams monitored the faint rhythmic pulse of its operational status, a digital heartbeat confirming that our creation was alive, but it was not yet speaking. It was listening, accumulating a portrait of the world beneath the ice, with a patience that bordered on the profound. It gathered echoes from the planet's core, measured the infinitesimal flecks of the crust under the ice's unimaginable weight, and recorded temperature variations 1,000 times more subtle than anything we could feel. Each sensor, a nerve ending in a continental-scale nervous system, was building its own piece of a puzzle so vast no single human mind could ever hope to assemble it. The supercomputers at the processing hubs in Boulder and Cambridge were the designated brain tasked with the colossal effort of weaving these trillions of disparate data points into a single coherent vision. They churned through the background noise, the seismic static of distant earthquakes, the gravitational pull of the moon, the steady, predictable chill of the ice itself, all in search of a signal. A signal that many in the scientific community believed would be vanishingly faint, perhaps even non-existent. The prevailing models, the consensus built over decades of research, told us that while some geothermal heat must exist, it was a background character in this story. A minor player contributing a gentle, almost negligible warmth, easily overpowered by the colossal influence of the warming oceans and atmosphere above. The real drama, we were told, was all on the surface. We were about to discover just how profoundly wrong that consensus was. The breakthrough did not arrive like a thunderclap. It came as a slow, rising tide in the data, an anomaly that at first seemed like an error in the system's calibration. It began in the subnetworks positioned deep beneath the catchment area of the Thwaites Glacier, that terrifyingly vast and unstable river of ice, whose collapse alone could trigger catastrophic sea level rise. The thermal probes designed to detect heat flux in milliwatts per square meter started to report values that were not just higher than expected, they were an order of magnitude higher. The initial reports were met with skepticism, a flurry of diagnostic checks and system reboots. It had to be a malfunction, a cascade of faulty sensors, or perhaps a solar flare interfering with the sensitive electronics. But the signals were not erratic. They were stable, persistent, and terrifyingly consistent across a wide geographic area. The system was not broken. It was showing us the truth. The supercomputers, guided by new parameters, began to render the first comprehensive thermal map of the bedrock beneath West Antarctica. As the image resolved on the screens, a collective intake of breath could be heard across control rooms on 3 continents. What appeared was not the cold, mostly uniform blue we had anticipated. Instead, the continent's hidden bedrock was streaked with angry reds and vibrant oranges, a ghostly image of a fire raging in a subterranean world. It was a cartography of a hidden inferno. This was not the gentle planetary warmth of a cooling core. This was something else entirely. Something focused, active, and alive. Staring out from the center of this thermal map was the Thwaites Glacier Basin, glowing with an intensity that defied all our previous understanding. Here, beneath 3 kilometers of ice, the 3I Atlas network revealed a region of geothermal heat flux that was not just anomalous, it was geological violence captured in the cold language of data. The numbers were staggering. In localized hotspots, the bedrock was radiating heat at over 200 milliwatts per square meter. To put that into perspective, the average for continental crust is around 65. Some of the zones we were seeing were hotter than the bedrock beneath Yellowstone, one of the most active supervolcanoes on the planet. We had been searching for a candle flickering in the dark, and had instead found a celestial blowtorch aimed directly at the soft underbelly of the world's most vulnerable ice sheet. This wasn't a gentle warming from below, this was an active and aggressive assault. The ice was not just being melted by a warming ocean at its edges, it was being cooked from the bottom up across an area larger than the state of Florida. The base of the ice, the critical interface where ice meets rock, was not a static frozen boundary. The data revealed it to be a dynamic, slushy and chaotic environment, a landscape of subglacial lakes superheated from below, and vast flowing rivers of meltwater, all driven by this immense and previously invisible engine of heat. We were watching the very foundations of the continent dissolve. This was the source of the lubrication, the film of water, that was allowing these continent-sized glaciers to decouple from their bedrock and accelerate their slide toward the sea. The models had always struggled to account for the shocking speed of glaciers like Thwaites and Pine Island. They had tweaked variables, adjusted friction coefficients, and theorized about meltwater dynamics, but the numbers never quite added up. There was always a missing energy source in the equation. Now we had found it. The real reason was not a single factor, but a devastating conspiracy between two worlds. The heat from our warming atmosphere and oceans was eating away at the ice from above and around the sides, while this ancient hidden furnace was gutting it from within. It was a two-front war, and the ice was losing on both fronts far faster than anyone had dared to imagine. The question immediately became, where was this colossal amount of energy coming from? The answer, it turned out, was written in the very architecture of the planet. West Antarctica sits atop one of the largest and most active continental rift systems on Earth. The West Antarctic Rift System is a massive, slowly unfolding geological event where the Earth's crust is being stretched apart like dough being pulled in opposite directions. For over 100 million years, this process has been thinning the continental plate, creating deep basins and allowing the planet's scorching hot mantle to bulge upwards, pressing ever closer to the surface. You can think of it as a scar on the planet's skin, one that never fully healed. In most places on Earth, the solid crust that insulates us from the molten interior is over 30, even 40 kilometers thick. But here, beneath the ice, the 3I, Atlas, seismic data, revealed a crust that was in some locations barely half that. It's a dangerously thin shield protecting the ice from the furnace below. This proximity of the mantle creates the perfect conditions for widespread volcanic activity and high heat flow. The network's gravimetric sensors confirmed this, detecting subtle variations in density that correspond to magma intrusions, plumes of molten rock that have risen and pooled just kilometers below the bedrock. We were not just looking at a hot spot, we were looking at a vast, interconnected network of them, a kind of thermal plumbing system that channels planetary heat directly to the base of the ice. The angry red streaks on our new map were the surface expressions of this deep, powerful system. They traced the fault lines, the fractures, and the thinnest points in the crust, revealing a hidden geography of fire that perfectly matched the geography of ice melt above. The discovery recast our entire understanding of Antarctica. It was not simply a passive frozen continent. It was a place of immense geological dynamism, a land of fire and ice in the most literal sense. A place where the internal fury of the Earth was directly engaged in a battle with the frozen relic of our last ice age. This revelation sent a shockwave through the climate science community. Decades of work, thousands of papers, and the foundational climate models that inform global policy were all built on an assumption. The assumption that geothermal heat was a negligible static background constant. It was a number plugged into the equations, a minor variable in a complex system dominated by external forces. But 3I, Atlas, proved that it is neither static nor negligible. It is dynamic, geographically concentrated, and in the critical regions of West Antarctica, it is one of the primary drivers of change. The old models were not wrong, they were simply blind. They were trying to predict the future of a melting fortress without knowing that an enemy was already inside the walls, setting fires in the basement. Our new data was the intelligence that changed the nature of the war. Suddenly, the alarming acceleration of the glaciers made perfect, terrifying sense. The models no longer needed to be forced to fit the observations. The observations now fit a new, more complete theory. A theory that included a planet actively working to shrug off its own ice. This internal heat does more than just melt the ice directly. It fundamentally alters the physics of the entire system. By creating that pervasive layer of meltwater at the base, it acts as a continental-scale lubricant. Imagine a block of ice sitting on a stone floor. It's stable. Now pour a thin film of water underneath it. Even the slightest push will send it sliding. We are not pushing the West Antarctic ice sheet, we are pulling it with warming ocean currents and melting its surface with a warmer atmosphere. But it is this geothermal heat, this constant, widespread source of basal lubrication, that has greased the skids. It has turned a stable, grounded ice sheet into a hydroplaning behemoth poised to slide into the ocean with terrifying efficiency. The friction that once held it in place, the immense gravitational anchor pinning it to the continent, is being systematically eroded from below by a force we never knew was there. The implications are almost too vast to fully comprehend. The rate of future sea level rise is one of the most critical and uncertain predictions in all of science. It affects coastal communities, global economies, and the fate of entire nations. And all of our predictions were based on an incomplete picture of the forces at play. We now understand that any model that does not accurately account for the dynamic, geographically specific geothermal heat flux beneath the ice is not just inaccurate, it is dangerously optimistic. The timelines for the potential collapse of key glaciers like Thwaites may need to be radically revised. The tipping points we feared were on the horizon may in fact be far closer than we thought, or we may have already passed them. This is not a force we can control. We cannot turn down the planet's thermostat. The heat from the West Antarctic rift system is a product of geological time, a process that began when dinosaurs roamed the Earth and will continue for millions of years after we are gone. It is a fundamental, unchangeable feature of our world. Its interaction with our rapidly changing climate is what has created this perfect storm, a confluence of internal and external forces that have placed a time bomb beneath the ice. For the scientists who had dedicated their lives to this project, this moment was a strange and potent cocktail of emotions. There was the profound exhilaration of discovery, the sheer intellectual thrill of seeing the unseen and solving a puzzle that had vexed science for generations. It was a triumph of human ingenuity, a testament to our relentless curiosity. But that exhilaration was chased by a cold, creeping dread. The dread of knowing that your greatest discovery is also a dire warning. The dread of understanding that the system is even more fragile, the situation more precarious, and the time to act even shorter than we had believed. The ghost in the machine was real. We had proven its existence. We had mapped its terrible fiery breath. We had found the engine of destruction, a planetary heat pump, working in concert with our own atmospheric warming to dismantle the world's greatest store of ice. The question was no longer what was causing the collapse. The question, now ringing with terrifying urgency in labs and government halls around the world, was how fast this process would unfold. Having finally understood the true nature of the enemy beneath our feet, could we now possibly predict its terrifying, unstoppable advance? And so the phantom haunting the ice was unmasked. Not the gentle ambient warmth of a planet's core, but a concentrated violent fever, a deep wound in the Earth's crust left by the 3I Atlas impactor, still bleeding heat after 1 million years. This geothermal furnace, a celestial blowtorch aimed at the underbelly of Antarctica, was the missing piece of the puzzle. But in finding it, we hadn't solved the crisis. We had merely uncovered the true terrifying scale of the siege. Because this internal fire, this ancient echo of a cosmic collision, was not fighting its war alone, it was being met by an accomplice, an enemy advancing from the outside, an invader of our own making. For the first time in planetary history, the ice sheet was being attacked from 2 directions at once, caught in a devastating pincer movement of heat. While the impact crater's thermal anomaly cooked the continent from its rock-bound foundations, our warming atmosphere and supercharged oceans were launching their own assault upon its coastal ramparts. This new enemy arrived silently, not as a raging storm, but as a subtle, insidious shift in temperature. You have to think of the Southern Ocean not as a placid moat, but as a complex, layered system of immense thermal power. For eons, the coldest, densest water has hugged the Antarctic coast, a protective shield of near-freezing brine that kept the great ice sheets stable. But our industrial age has re-engineered this system. The surface waters, warmed by a thickening blanket of greenhouse gases, are now transferring their excess energy downward. Worse still, changing wind patterns themselves, a consequence of a warming planet, are physically pushing this warmer surface water deeper and driving a relentless current of comparatively warm, salty circumpolar deep water directly toward the continent's edge. This water, though only a few degrees above freezing, is a thermal behemoth to an ice sheet accustomed to absolute cold. It carries more destructive energy than 1,000 hurricanes, and it is now being aimed with terrifying precision at the most vulnerable points of the ice sheet, the grounding lines. The grounding line is the sacred boundary, the last line of defense. It is the precise invisible seam where the colossal weight of a glacier flowing off the continent finally lifts off the bedrock and begins to float upon the ocean. For millennia, this boundary was a place of equilibrium, a slow, patient negotiation between the forces of ice and sea. But now it has become a battlefront, a ground zero for planetary change. Imagine the scene miles below the surface in a realm of crushing pressure and absolute darkness. From below, seeping through the rock, comes the geothermal heat from the 3I Atlas scar. It doesn't boil the water, not under this immense pressure. Instead, it creates a super-pressurized layer of meltwater at the very base of the ice, a lubricant that reduces friction and eases the glacier's slide toward the sea. This alone is a grave threat, a subtle loosening of the brakes. But then comes the second wave of the attack. That warmer circumpolar deep water, dense and heavy with salt, intrudes with inexorable force. It pushes past the floating ice shelf and finds its way right to that critical grounding line. Here, in this crucible of forces, the two sources of heat meet, and their interaction is not additive, it is multiplicative. The geothermally warmed basal meltwater, being fresh, is less dense than the salty ocean water. It wants to rise. The warmer, saltier ocean water is denser than the fresh surface melt, but less dense than the coldest bottom waters it has displaced. It wants to sink and spread. This creates a violent, chaotic mixing, a subglacial vortex of thermal devastation. The ocean water, already supercharged with heat from our atmosphere, prevents the basal meltwater from refreezing. The constant flow of fresh meltwater in turn accelerates the melting caused by the ocean intrusion. It's a perfect, catastrophic synergy. The internal heat weakens the ice from its foundation, and the external heat exploits that weakness, carving away at it with horrifying efficiency. The very chemistry of the water conspires against the ice. The intense pressure at these depths dramatically lowers the melting point of the ice, allowing it to be eaten away by water that would feel merely cool to the touch at the surface. We are not just melting Antarctica, we are dissolving its foundations from the inside out. The result of this combined assault is the birth of something monstrous, something our models had never predicted because they never accounted for the internal fire. We are creating vast, unseen worlds beneath the ice. As the grounding line is attacked by this dual-front thermal war, it doesn't just retreat uniformly. It is eaten away from beneath, hollowed out. The process begins a vicious cycle, creating enormous sub-ice cavities, cathedrals of darkness carved by warm, swirling water. These are not small pockets of melt. Satellite-mounted ice-penetrating radar, cross-referenced with the new geothermal maps from Project Atlas, has revealed their true terrifying scale. In the Amundsen Sea sector directly over the hottest zones of the 3I, Atlas crater's residual heat, we have found cavities tens of miles long and thousands of feet high. Imagine the Grand Canyon submerged in an eternal churning twilight, with a ceiling made not of rock but of groaning, cracking, dissolving ice. This is what we have created. These are entire mountain ranges of negative space secret oceans growing in the heart of the continent. Within these new subterranean voids, the laws of physics turn against the ice with even greater fury. As a cavity expands, it creates more surface area for the warm ocean water to attack. A flat, stable grounding line becomes a complex three-dimensional labyrinth of ice cliffs, tunnels, and pillars, all being melted simultaneously. The geothermal heat from the bedrock below continues its work, ensuring the base of these cavities remains a slurry of meltwater, preventing any chance of the glacier regrounding or finding a new point of stability. The water inside these caverns is not static. It forms powerful self-sustaining convection currents. Meltwater from the ice ceiling, being fresh and slightly less dense, rises. The warmer, saltier ocean water flowing in from the front sinks to the cavity floor, where it continues to scour the bedrock and attack the base of the ice. This creates a relentless circulating engine of destruction, a ghost river system carving canyons in the dark, constantly pulling in more warm ocean water from the outside to fuel its work. We can now see the signature of these hidden worlds from space. Using interferometric synthetic aperture radar, scientists can measure the rise and fall of the ice sheet's surface with millimeter precision. They can literally see it breathing with the tides. Over a stable, grounded glacier, this motion is minimal. But over these newly discovered cavities, the ice surface flexes and sinks, rising and falling tens of feet. The ice is no longer anchored to the continent. It is a sagging, brittle roof over a vast, growing chamber of water. This flexing action further weakens the ice, creating and expanding crevasses and fractures that can penetrate for miles, compromising the structural integrity of the entire glacier. We are transforming what was once a solid monolithic shield of ice into a fragile, hollowed-out shell. The foundations are being systematically removed, leaving trillions of tons of ice supported by nothing but its own cracking, failing internal strength. The very weight of the glacier, which once held it in place through friction, now becomes its greatest enemy, pulling it apart from the inside. This brings us to the most terrifying discovery of all the feedback loop. What we are witnessing is not a linear, predictable process of melting. It is a runaway, self-amplifying cycle of collapse. Step 1. The combination of geothermal heat and warming ocean water creates a sub-ice cavity at the grounding line. Step 2. This larger cavity allows a greater volume of warm circumpolar deep water to penetrate deeper beneath the ice sheet, far beyond the original coastline. Step 3. This increased volume of warm water melts the ice base at a dramatically accelerated rate, expanding the cavity further and faster. Step 4. The expanding cavity and accelerated basal melt reduce the friction between the ice and the bedrock, effectively lubricating the glacier's path. The brakes are gone. This causes the glacier to speed up stretching and thinning it, which makes it even more vulnerable to fracture. Step 5. The faster flowing glacier draws even more ice from the continent's interior, committing vast, once stable reservoirs of ice to this irreversible process of collapse. This entire sequence then repeats, but each cycle is faster and more destructive than the last. The larger the cavity, the more heat it can draw in. The more heat it draws in, the faster the cavity grows. It is a serpent eating its own tail, a thermal engine that feeds on its own destruction. The geothermal anomaly from the 3I Atlas impact created the initial vulnerability, the strategic weakness in Antarctica's defenses. It pre-softened the target. Our anthropogenic warming has provided the weapon an endless supply of warm ocean water to exploit that weakness with devastating force. We have unwittingly armed the ocean and aimed it at the continent's weakest point, a point predetermined by an astronomical event 1,000,000 years ago. This is no longer just about melting, it is a fundamental change in the physics of the system. We have pushed Antarctica past a tipping point. The grounding lines of the major West Antarctic glaciers, like Thwaites and Pine Island, are not just retreating, they are being annihilated. They are caught in a gravitational trap from which there is no escape. For decades, our climate models treated the Antarctic ice sheet as a mostly solid block reacting slowly to external changes in air and sea temperature. They were sophisticated, but they were missing the fire beneath. They saw the symptoms, the accelerating glaciers, the thinning ice shelves, but they misdiagnosed the disease. They were trying to understand a house fire without knowing someone had poured gasoline on the foundations. The 3I Atlas discovery has forced us to tear up those old models. The rates of decay we are now witnessing are not just exceeding the worst-case scenarios, they are happening for reasons we never before had the imagination to consider. The problem is far more complex, the danger far more immediate. We are not just fighting the warming we create today. We are fighting the combined power of our own industrial emissions and the residual concentrated energy of an asteroid strike that shook the world long before the first human ever walked the Earth. The ice, which we once saw as a static, permanent feature of our world, is revealing itself to be a dynamic and terrifyingly fragile system. It groans under the strain. Satellites listen to its seismic shudders as vast internal structures collapse into the hidden oceans below. We watch its surface speed up the flow of ancient ice, accelerating from inches per day to miles per year, a silent, unstoppable avalanche unfolding over decades. We see the final catastrophic consequences as the weakened ice shelves, no longer buttressed by a stable grounding line, finally disintegrate in colossal calving events. But these spectacular breakups, the icebergs the size of cities that capture the world's attention, are not the main event. They are merely the final dying screams of a battle that was already lost far away and deep beneath in the dark, warm waters of the cavities we helped to create. The discovery of this synergistic destruction has thrown the scientific community into a state of emergency. Every old assumption must be re-evaluated, every calculation rerun. The crucial question is no longer if times Antarctica will contribute to sea level rise, but how fast and how much. The great ice sheet, once a sleeping giant, has been awoken by a fever from within and an assault from without. It is bleeding into the ocean, and we now understand that the wound is far deeper and more complex than we ever knew. We are watching the deconstruction of a continent in real time. And the urgent, terrifying question that now hangs over every coastal city, every island nation, every person on this planet is this: how do you stop a runaway train that is being pushed from behind while the tracks in front of it are being dissolved? How do you fight a war that is already lost? And so, the phantom was unmasked. The ghost in the machine, the anomalous heat bleeding through Antarctica's bedrock, finally had a name: 3I, Atlas. But to give a monster a name is not to tame it. The discovery wasn't an answer, it was the beginning of a far more terrifying question. Finding the source of the fire was one thing, understanding how it was actually burning down the house from the foundations up was another entirely. For centuries, our vision of Antarctica was deceptively simple, governed by a straightforward thermal equation. We watched the sky, we measured the air, we tracked the sun's glare on the endless white surface. We believed the Great War for the ice was fought from above a battle between solar radiation and atmospheric temperature. The continent's frozen heart we assumed was safe, insulated by its own colossal mass resting upon a cold, dead geologic slab. The 3I Atlas data shattered that illusion with the force of a tectonic plate. The real threat, the primary existential danger to the ice, was not descending from the heavens. It was rising from the deep earth. The implications were staggering, forcing us to discard generations of glaciological models and confront a new, deeply unsettling reality. We were looking in the wrong direction. The entire time we were staring at the roof, a planetary furnace had been switched on in the basement. This wasn't the explosive, violent heat of a volcano, a singular plume of magma punching its way through the crust. That kind of thermal violence is easy to spot, a geological scream that echoes through seismometers. No, this was something far more insidious. Think of it not as a celestial blowtorch, but as a continental-scale hot plate, a vast and diffuse zone of warmth being conducted silently upwards through miles of ancient rock. The energy from the 3I Atlas anomaly doesn't erupt. It seeps. It radiates with a slow, inexorable patience, warming the bedrock by just a few crucial degrees over an area larger than many nations. At the surface, under the thin air of the Antarctic plateau, a few degrees is trivial, lost in the overwhelming polar cold. But here, at the bedrock interface, 3 kilometers below the ice, those few degrees are the difference between solid and liquid, between stasis and collapse. For here, another force comes into play, an invisible ally to the geothermal heat pressure. The crushing weight of the ice sheet above is almost beyond comprehension. Imagine the entire weight of a mountain range pressing down on every square meter. This immense pressure alters the very laws of physics. It lowers the melting point of water ice, making it easier for the solid H2O to transition into its liquid state. The ice at the base of the sheet is already on a knife's edge, primed and ready to change. The gentle, persistent warmth from below is the final decisive push it needs. And so, in the absolute darkness, under a pressure that would crush a submarine like a tin can, the great melt begins. It starts not as a flood, but as a whisper. A single molecule of ice trapped for 1 million years feels the latent heat in the rock beneath it and shudders, breaking its crystalline bonds. It becomes a microscopic bead of water. It is joined by another and another. A billion-year-old geological process gives birth to a single perfect drop. This process repeats trillions upon trillions of times across thousands of square kilometers of the ice sheet's base. The water coalesces, forming a thin, lubricating film between the ancient enemies of rock and ice. This is the genesis of a world we never knew existed, a vast hidden hydrosphere sealed away from the sun and the sky. As the melt continues, fed by the unending warmth of 3I, Atlas, this basal film thickens. Gravity and pressure begin to sculpt it. The water seeks the lowest points in the subglacial topography, pooling in ancient valleys and basins that have not seen daylight since before humanity evolved. This is how a subglacial lake is born. Using ice-penetrating radar and subtle seismic surveys, which allow us to listen to the continent's hidden pulse, we have mapped these impossible bodies of water. They are colossal. Some are the size of great cities, others as large as inland seas, all interconnected by a complex plumbing system we are only just beginning to comprehend. For decades, we thought these were isolated phenomena, geological oddities like Lake Vostok, but the data flowing from the 3I Atlas investigation reveals something new, a dense, sprawling network of lakes and reservoirs, a veritable subglacial archipelago, all being actively fed and warmed by this deep earth heat source. These are not stagnant ponds, they are the beating heart of Antarctica's hidden circulatory system. A lake, however, can only hold so much. As the geothermal furnace continues its work, relentlessly converting solid ice into liquid water, the pressure within these subglacial reservoirs builds to incredible levels. The water must go somewhere. Squeezed by the immense weight from above, it is injected into the surrounding landscape with the force of a hydraulic press. It finds the weakest points, the tiniest fractures at the base of the ice, and begins to carve. It becomes a liquid razor, etching channels and conduits connecting one lake to the next. What forms is not a gentle, meandering creek, but a high-pressure, high-velocity river system, a network of arteries carrying meltwater across the continent in absolute blackness. These rivers can be enormous, carrying volumes of water that would rival the Amazon, and they can flow with astonishing speed. Scientists have detected them by observing the subtle rise and fall of the ice surface above, by mere millimeters, as great pulses of water, known as subglacial flood events, surge from one lake basin to another. We are witnessing the creation of an active continent-wide drainage basin where none was thought to exist. This network acts as a superhighway for meltwater, efficiently collecting the product of the geothermal melt from the deep interior of the continent and transporting it with terrifying efficiency hundreds of kilometers towards its ultimate destination, the sea. And in doing so, it has become the ultimate agent of continental instability. Ice sheets are not static monoliths. They are in fact the world's slowest and largest rivers. They flow. Under their own colossal weight, they deform and creep towards the coast where they break off as icebergs. For millions of years, this process was held in check by friction. The base of the ice, particularly where it was frozen solid to the bedrock, acted as a powerful brake, slowing this inexorable march to the sea. But the water from the 3I Atlas anomaly has fundamentally changed this dynamic. The vast network of lakes and rivers created by the geothermal heat serves as a perfect continent-scale lubricant. It decouples the ice from the rock below. That immense friction is lost. The great ice streams that drain Antarctica's interior behemoths, like the Thwaites and Pine Island glaciers, already considered the continent's weak underbelly, are now sliding on a film of geothermally warmed water. They are no longer grinding their way to the ocean. They are hydroplaning. Our satellite observations confirm this with chilling precision. The flow rates of these critical glaciers have not just increased, they have accelerated, dramatically doubling, and in some places tripling in just a few decades. We are watching the brakes fail on a multi-quadrillion-ton vehicle, and it is picking up speed as it heads downhill. This single mechanism, this basal lubrication driven by the heat of 3I Atlas, was enough to rewrite our understanding of ice dynamics. But the story does not end there. The system had one more terrifying secret to reveal, a final act of synergy that combines the internal heat with an external threat, creating a nightmare scenario of runaway collapse. The subglacial rivers, having journeyed hundreds of kilometers from the heart of the continent, finally reach the coast. Here, the ice sheet extends out over the ocean, forming immense floating platforms of ice known as ice shelves. These shelves act like a cork in a bottle, buttressing the glaciers on land and physically slowing their flow into the sea. They are the single most important stabilizing feature on the continent, and it is here that the true horror of the dual-driver melt is unleashed. The high-pressure rivers flowing beneath the land-based ice do not simply stop at the coast. They continue to flow, carving channels not into the rock, but into the underside of the floating ice shelf itself. They emerge from under the grounded ice sheet as plumes of relatively fresh, buoyant meltwater, gouging out vast canyons and inverted valleys in the ice shelf's belly. These channels, carved from within by the continent's own meltwater, become perfect conduits, veritable superhighways for a different, even more dangerous enemy to penetrate the system. Lurking in the deep ocean is a layer of comparatively warm, salty water known as circumpolar deep water. For millennia, this water was held at bay by the sheer frozen mass of the ice shelves, but now the channels carved by the subglacial rivers have created deep recessed pathways. They have opened the door from the inside. The dense, warm ocean water pours into these new channels, penetrating tens, even hundreds of kilometers further inland than was ever thought possible. It floods the deepest parts of the ice shelf, cavities, making direct contact with the grounding line, the critical juncture where the land-based ice first begins to float. This is the Achilles heel of the entire ice sheet. The geothermal heat from 3I, Atlas, melts the ice from below, creating the very rivers that then carve the channels that allow the warm ocean to invade and attack the ice sheet at its most vulnerable point. It is a catastrophic feedback loop, an internal wound that invites an external infection. This is the dual driver melt scenario, a 1-2 punch from the planet itself. The heat from below weakens and accelerates the ice, while the ocean from without melts its critical foundations. One driver creates the opportunity for the other, and together their combined destructive power is exponentially greater than the sum of their parts. The discovery of this mechanism sent a shockwave through the global scientific community. It was a paradigm shift so profound it bordered on a crisis. The predictive models for sea level rise, the complex algorithms running on the world's most powerful supercomputers, were suddenly terrifyingly obsolete. They were masterpieces of atmospheric science, of oceanography, of surface glaciology, but none of them, not one, had accounted for a continental-scale hotplate churning out a lubricating river system that actively invites the ocean in to eat away at the ice from beneath. It was like trying to predict the trajectory of a cannonball without knowing about the existence of gunpowder. All the calculations were elegant, sophisticated, and fundamentally wrong. A frantic, desperate scramble began. Teams in Boulder, in Cambridge, in Potsdam worked around the clock trying to code this new terrifying physics into their models. They needed to simulate the heat flow through the bedrock, the thermodynamics of basal melting under pressure, the fluid dynamics of subglacial rivers, and the complex, turbulent mixing of that fresh water with invading seawater. It was an undertaking of Herculean complexity. As the first results from these new recalibrated models began to trickle in, a stunned silence fell over the community. The numbers were catastrophic. Projections that had once spoken of sea level rise over centuries were now talking about the same changes happening in mere decades. The potential rates of collapse for the West Antarctic ice sheet were no longer linear and predictable, but could be rapid, chaotic, and irreversible. The carefully constructed timelines upon which governments and economies had based their climate adaptation strategies were exposed as wishful thinking. The polite academic language of scientific papers gave way to urgent, stark warnings. The words tipping point and runaway collapse moved from the realm of distant possibility to imminent threat. The numbers on the screen were no longer abstract data points. They were a death sentence for coastlines around the world. They represented the drowning of entire cultures, the displacement of hundreds of millions of people, and the redrawing of the world map. The discovery of 3I, Atlas, had done more than just solve a geophysical mystery. It had reset the clock on the climate crisis, revealing that the fuse on Antarctica's time bomb was burning far, far faster than anyone had ever dared to imagine. We were not just facing a future of rising seas, we were facing a deluge of our own making, supercharged by the ancient hidden heart of our own planet. The fate of our coastal cities, our economies, our very civilization now hinges on understanding the full implications of this fire beneath the ice. The ice sheet is no longer a sleeping giant. It is awake, it is moving, and thanks to the phantom heat of 3I, Atlas, it is now sliding ever faster towards the sea. Our journey together began with a simple yet terrifying observation. A vast continent of ice, a planetary thermostat holding back the sea, was bleeding into the ocean at a rate that defied all our calculations. We pointed to the warming air above, and the warming waters lapping at its edges, certain we had identified the culprits. And we were right, but we were not completely right. The story we have discovered is infinitely more complex, its origins buried miles beneath the frozen surface, written in a language of heat and pressure we were only just beginning to decipher. We were looking at the patient's fever, but we had missed the infection raging deep within. What 3I Atlas has given us is not just another dataset. It is a new sense of perception, a key to a locked room in our own home. For decades, our climate models treated Antarctica as a colossal but fundamentally passive block of inert ice. It was a victim of external forces, a white mirror reflecting the sins of an industrializing world. We measured the meltwater, we tracked the calving icebergs, and we drew our trend lines towards a distant, troubling future. But the satellite, with its revolutionary interferometric radar, its gravity gradiometers, and its infrared eyes, forced us to abandon this comfortable, simplistic image. It allowed us to feel the continent's pulse for the very first time, and what we found was a world away from the inert ice block of our imagination. We found a continent that was alive, a continent with a hidden metabolism, a secret fire. The heat map it returned was not a uniform cold blue, but a stunning, terrifying mosaic of deep reds and searing oranges. These were the hotspots, the geothermal flux anomalies, the previously invisible wounds where Earth's primordial heat leaks through the crust, creating a network of subglacial blowtorches. The East Antarctic rift system, once a subject of geological curiosity, was revealed to be a gaping vulnerability, a 3,000 kilometer-long scar, weeping thermal energy directly onto the base of the world's largest ice sheet. We saw how this heat lubricates the ice from below, creating vast unseen rivers and lakes of meltwater that decouple the ice from the bedrock itself. This hidden plumbing system acts as a continent-wide conveyor belt, accelerating the flow of ice streams like the Thwaites and Pine Island glaciers towards their final fatal rendezvous with the ocean. This discovery represents nothing less than a paradigm shift in our understanding of cryospheric dynamics. It fundamentally recalibrates the clock on Antarctic collapse. The ice sheet is not just melting, it is being actively undermined from its very foundation. Think of it not as an ice cube left out in the sun, but as a frozen castle built upon a simmering volcanic field. For millennia, a delicate equilibrium existed. The immense pressure of the ice cap above largely contained the heat below, and the surface cold balanced the geothermal warmth. But this balance was precarious, a geological truce we have now broken. The external warming from anthropogenic climate change was the first shot fired in a new war against the ice. As the atmosphere and oceans warm, they thin the ice from above and around the edges. This thinning lessens the immense pressure on the bedrock below, a process known as isostatic rebound. And as the pressure eases, it's like lifting the lid on a planetary pressure cooker. The geothermal heat flow intensifies, able to escape more easily. More basal ice melts, which provides more lubrication. The glaciers accelerate their march to the sea, which thins them further. And so the cycle continues, a devastating feedback loop that our previous models were utterly blind to. We were watching a house burn, unaware that someone had already soaked the foundations in gasoline. The 3I Atlas data forces us to rewrite the textbooks, to throw out the old linear projections of sea level rise and replace them with models that account for these terrifying non-linear accelerants. The future is no longer a gentle, predictable slope. It is a landscape of tipping points and sudden catastrophic cliffs. It is absolutely crucial, however, to understand what this discovery does not mean. It does not exonerate humanity. It does not shift the blame for our melting world onto the planet itself. The Earth's internal heat is a geological constant, a background condition that has existed for eons. It is the stage upon which the final act of this climate drama is being set. But we wrote the script. We are the ones who have turned up the stage lights to a blistering intensity. Anthropogenic climate change, driven by our relentless emission of greenhouse gases, remains the primary driver, the overarching existential threat. It is the warming atmosphere, and most critically the warming Southern Ocean, that are eating away at the ice shelves, the vital doorstops that hold back the continent's land-based glaciers. The geothermal flux is the accomplice, the unseen co-conspirator. It's the traitor within the gates, weakening the castle's foundations while the enemy army masses outside. One threat without the other would be manageable, a slow siege. But together they create a perfect storm of planetary deconstruction. The external heat attacks the defenses, while the internal heat mobilizes the glaciers for a faster retreat. This new knowledge does not offer us an escape clause from our responsibility. It hands us a more urgent and complex indictment. We now know the system is far more sensitive, far more vulnerable than even our most pessimistic scientists had dared to imagine. The safety buffer we thought we had, the decades we thought we could use to get our house in order, has been drastically reduced. The fuse has been burning all along, and 3I, Atlas, has revealed that it is far shorter than we ever knew. So, where do we go from here? Armed with this beautiful, terrible new clarity, the era of ignorance is over, and with it the luxury of inaction. Our first imperative is to continue watching, to never again look away. 3I, Atlas, was a pathfinder, a revolutionary first glance. But it cannot be the last. We need a continuous high-resolution presence over the poles, a successor mission that can track these changes not year by year, but month by month, week by week. We must map the subglacial plumbing of Antarctica with the same precision we map the streets of our own cities. We need to drill down through miles of ice, deploying robotic probes into those hidden lakes and rivers to understand their chemistry, their temperature, their flow. This is the scientific frontier of the 21st century, a challenge that will demand unprecedented levels of international collaboration. The Antarctic Treaty System, a remarkable legacy of Cold War cooperation, must now evolve into a framework for planetary survival. The data from these future missions cannot be firewalled by national interest. It must be a global commons, an open source warning system for all of humanity. Because the fate of Antarctica is not a regional issue, the meltwater from its shores does not stay in the Southern Ocean. It is a global pulse of fresh water injected into the world's circulatory system, altering ocean currents, changing weather patterns, and redrawing the maps of our world. The fate of a coastal city like Miami, of low-lying nations like Bangladesh, of historic capitals like Venice and Amsterdam is being written right now in the unseen interaction between rock and ice 10,000 kilometers away. This knowledge compels us to adapt, and to do so with an urgency that reflects the new reality. For decades, we have spoken of mitigation, of reducing emissions to prevent the worst impacts of climate change. That fight remains more critical than ever. Every fraction of a degree of warming we can prevent is buying precious time for the ice, slowing the feedback loops that 3I, Atlas, has so vividly revealed. But we must now accept that a certain amount of sea level rise is no longer preventable. It is already locked into the system. The heat we have already put into the oceans will continue to gnaw at the ice shelves for centuries. The destabilization of glaciers like Thwaites may already be irreversible. Adaptation, therefore, is not a sign of defeat. It is a pragmatic and necessary response to the world we have created. It means redesigning our coastal infrastructure. It means planning the managed retreat from shorelines that can no longer be defended. It means building a global financial and humanitarian framework to support the communities and nations on the front lines, those who will pay the highest price for a crisis they did the least to cause. It means rethinking our relationship with the ocean itself, seeing it not as a static boundary, but as a dynamic and rising force. The images sent back by 3I, Atlas, are in the end a profound reflection of ourselves. They show us a system of immense power and beauty, a world of breathtaking complexity pushed to its breaking point. They are a warning etched in the language of physics and light that the consequences of our actions are now manifesting in the most remote and seemingly untouchable places on Earth, but they are also a testament to our own potential. Our species, capable of destabilizing a planetary system, is also the species that can build a machine to fly 500 kilometers above it, to peer through miles of solid ice, and to comprehend the truth. The same ingenuity that fueled our industrial ascent now offers us the only path forward. Our journey across the ice has brought us face to face with a deeply unsettling reality, one that challenges our sense of security and demands a profound transformation in how we live on this planet. The great white continent at the bottom of the world is no longer sleeping. It is stirring, awakened by the heat from above and below, and in its awakening it is sending us a clear, unambiguous message. The time to act was yesterday. The next best time is now, undefined.